Hello everyone, welcome to Code and Learn. In this video, we are going to learn about big O notations. We will cover the formal definition of big O notations, that is the mathematical way of describing big O. We will also cover examples of common big O notations. Then we will also look at different big O notations and their graphs to understand how their performance is. At the end, we will also look at code examples for big O notations. So let's get started. So what exactly are big O notations? The big O notations are used to describe the time complexity of an algorithm. It can be seen as the proportionality of the number of steps taken by an algorithm to the number of elements in a data structure. So how you would describe the number of steps taken by the algorithm in relation to the elements. That is a big picture overview of big O notations. For example, an big O notation of On represents that the time taken by the algorithm that we are looking at is proportional to the number of elements, where the number of element is n. So that means the more elements there are in the data structure, the greater will be the time taken by the algorithm. That is, it increases with the number of elements and then decreases if the number of elements are decreased. A common example is a linear search algorithm. For example, if we have an array of 5 elements and you want to search an element in the array, you would have to go through all the elements to search for it. If the array has 100 elements, you would have to go through them to search for the element we are looking for. So the number of steps taken in the first case was 5, or the max number of steps taken by a linear search in first case was 5. And if we increase the number of elements to 100, the max steps taken by the algorithm is 100. So you can see there's a direct proportionality between the number of elements in the array, that is n, to the number of steps the algorithm takes, which is why we say it's O of n. Ideally, we would aim for a time complexity of O of 1. O of 1 represents constant time. That is, no matter how many elements there are in the data structure, the algorithm will always take the same time or constant time to perform the operation each time. So whether there are 10 or 1000 elements, the time complexity is same. That is, it only takes one step. We also use the big O notation for space complexity. That is, getting a sense of how much space the algorithm will take to perform the operation. Now the question is, why do we use big O notations? This is because getting the time complexity as proportionality of step is a better measure instead of comparing the times directly. So if you have a bigger computer, comparing the time with smaller computer may not give you the measure of how the algorithm is performing. On your bigger computer, it can take 1 nanosecond, which may make you feel that it is a fast algorithm. But when you go on to a smaller computer with less computing power, it can take up to 100 milliseconds, which in computer time is great value. So instead of looking at the time directly, we look at the number of steps, which helps you gauge the performance of the algorithm irrespective of the type of the machine. Here is the mathematical description of big O notation. It describes the upper bound of the growth rate of a function, or that if function gx grows no faster than function fx, then g is said to be member of OF. Or in simpler terms, it tells you how fast a function grows or declines. The letter O is used because the rate of growth of a function is also called the order of operations. Here we have an example. When analyzing some algorithms, one may find that the time or the number of steps it takes to complete a operation for a data structure of size n is given as 4n 2 minus 2n plus 2. When calculating the big O notation, we ignore the constant, that is, we can ignore 2, which makes sense because those depend on a particular hardware the program runs on. We also neglect the slower growing terms, that is, minus 2n. This is because the growth rate of this is a lot faster than this. So when the value of this section increases, this becomes negligible. So in that sense, we can say Tn grows at the order of n square. We can write the big O notation as O of n square. That is, we can say Tn grows in the order of n square. So that will be the time complexity of this solution. Now here we have a graph which shows you the growth rate of different big O notation. On the x-axis, we have the number of elements growing from 0 to infinite, and on the y-axis, we have the number of operations, which is 0 to infinite or infinity. As you can see, algorithms with time complexity of O log n or O of 1, which is constant time, are some of the best algorithms because the order of operation or the increase in order of operation is negligible. The best one of these is O of 1, which is constant time. That is, the runtime doesn't depend on the input size. One example of this is accessing an element of an array, which is always of constant time. The next best we have is logarithmic time, which is log n. The runtime grows logarithmically with the input size. One example of this is binary search. Next, we have linear search or linear time algorithms, where the runtime grows linearly with the input size. So the greater the size of the data structure we are working on, the greater will be the time complexity. A little worse than this is the linear arithmetic time, that is n log n, which is a combination of linear and logarithmic growth. Example of this is merge sort. As we go above, you can see we are approaching algorithms that have a bad O of n. An example here is quadratic time. The runtime grows quadratically with input size. And a common example of this is a loop inside a loop or nested loops. These algorithms are performance-wise really bad. Then we have the exponential time. That is, the runtime grows exponentially with the input size. So to recap, these are some of the best working algorithms. So we can say these are best. Then this is a good time complexity, followed by bad and some really bad time complexities. So whenever we devise an algorithm, we aim for O of 1, which is constant time operation. But practically, this is not usually something that we can achieve, but we always try to keep complexity in the green section here. Now one thing to note is when we talk about big O, we usually talk about the worst case scenario. For example, in linear search, if the element you are looking for is always the first element, the time complexity of this solution will be O of 1, that is constant time. While the worst case would be when the element is the last index in the array, and for that the time complexity will be O of n. So the best case is O of 1, while the worst case is O of n for a linear search algorithm. Now in the last lesson we looked at binary search. Binary search has a big O notation of O log n. In simple word, it means that you have to increase the algorithm step or the number of steps taken by the algorithm by 1 every time the data in the array is doubled. Let's understand this with the math behind it. Logarithms are opposite of exponents. For example, you have to multiply 2 by itself 3 times to get the answer 8. So log of 8 is 2, or log base 2 8 is 3. Similarly, we can say if log of 64 is 6, that means log to the base of 2 of 64 is 6. Another way of explaining the logarithm is how many times you need to divide 8 by 2 to get 1. The answer is 3. Now for binary search, we said the efficiency is O log n, where n is the number of elements in the array. This means if there are 8 elements in the array, the algorithm will take at max 3 steps. And if there are 16 elements, the algorithm at max will take 4 steps. So every time you are doubling the number of elements in the array to look for, the number of steps is only increasing by 1. So it means that the algorithm takes as many steps as it takes to keep halving the data elements until we remain with 1. This is usually a time complexity of a divide and conquer algorithm like binary search. Now to summarize, big O notations focuses on the behavior of a function as n approaches infinity. That is more of a mathematical definition. Then big O notation also provide a upper bound on the growth rate of a function. Keep in mind that the constant terms are ignored. They don't play a role in the growth rate of the overall function. And as we saw with the examples, the highest order term in a function usually determines its big O complexity. So that's it for this lesson. I hope you enjoyed it. If you have any questions, please post a comment under the video or reach out to our Discord server. Until next time, happy coding.